All right, so exactly. So this is the work, some of the work that I did during the PhD. Matthias Hauswirth was my advisor there in Lugano on the Università della Svizzera Italiana, and Johan Juri was a co-author in this part of the work that I did there from Utrecht. And yeah, so I'm going to talk about sound notional machines. So sound in the sense of sound argument, sound logical argument, right? And of course, this word is, we have soundness is progress plus preservation, right? So I was actually a little bit reluctant originally to use this word because it's like it looks like you're using a bazooka, something sort of, you're evoking something so well established. But I figured that this is, sort of probably a good word in this context here. And then I'm going to talk more about this. Okay, so. Okay, that was, we're getting started. Okay, this is interesting. Let me see. Okay, good. So this is my, well, never mind. So, you know what? Let me close it. I don't know how, no, I'm going to be moving slides enough, but no, it's going to be fine. It's going to be fine. Everything's fine. So, exactly. So notional machines. Anybody here heard this term before? And yeah, good. So this is it's something that is it's a well sort of known thing in the context of computing education, right? So essentially, this work is like let's say. As I used to say, it's sort of SIGPlan meets SIG-CSE, So the computing computing education sort of conferences are on one side, and then you have the SIGPlan conference on the other side, and we're sort of trying to connect these things. So in computing education, there is this research on notional machines. So for example. What is called an expression tree, right? So you have an expression, we know it forms a tree, and then maybe you're teaching this, you're teaching expressions to the people that are learning how to program, and then you could use a diagram to show how an expression sort of forms a tree. But another common thing is what is called, in the general sense, a memory diagram, right? So this is kind of maybe one of the most sort of popular tools, Python tutor, but it also works not only for Python but other programming languages, right? So you could draw it by hand, a memory diagram to show during a program execution what is the memory like, or you can use a tool, for example, that sort of steps through a program, and then and there are various kinds of things like this. But you also have things like it's not only diagrams. So you have things like this is an activity that Matthias does in so I TA'd his course there. There's a course, Programming Fundamentals 2, is like an introductory Java course that I TA'd for many years, and Matthias has been teaching like for, I don't know, over 10 years. And he does this activity early on where there's like a row of students, and then he wants to talk about recursion and say, well, say that each one of you is an instance of an object, and you want to sort of, and you're connected for example, in a line in an amusement park, and you want to say, well, instead of having to walk the whole thing, what would you do to kind of know how many people are in the queue, right? Or I mean, we don't use the word queue exactly so that it's not going to be with the wrong meaning, but you have a line of people, and then we maybe the students come up with a suggestion, maybe, and eventually you get to this idea that, well, you only need to talk to your neighbor student, and you ask, well, how many are there? And then the next one asks how many are there, and then you kind of go, and then you go back and you add up the numbers, and you can sort of, do this sort of, adding on the way back, or you can sort of add on the way down, right? And so there are a few things that you can do this. So you see that we had there sort of diagrams, and you had this kind of like, an entity an activity where the students are part of it, and then you can have other things like, so this is, I don't know if it's called a domino computer. So you have, okay, cool. This is really cool. So, you can arrange domino pieces in a way that they work like logic gates, right? And so, for example, if these are the inputs and that is the output, dominoes falling, it's a 1, so it's a signal is going through, and not falling is 0, and then this pattern is going to then behave like these gates. And there, a few years back, so this we did there was like the 10-year anniversary of the faculty there, and then this was Nate Nystrom's team, Amanj, Noshin, etc., the PhD students. I helped it a little bit. This was like a 3x4 3-bit adder, and this was kind of an outreach event there. So there were sort of, the different groups would sort of come up with activities for the public, and and we sort of had this in a big hall, and sort of we'd ask people to give the notes. We spent the whole day sort of building to run it once, and so that's pretty cool. And so what we have is so in general you could say, well, notional machines are these pedagogic devices that you use to assist the understanding of some aspect of programs and programming, right? So this aspect could be memory or references or mutation, or it could be expressions. And this is, this definitely. So the early uses of this term notional machine are from the 80s, and normally you're still going to find this sort of people using this word to refer to different things, right? And sometimes, originally it was more to talk about runtime semantics, essentially, but the more sort of modern, I think, view of it is this. And actually, the original, the terminology was coined by Duboulay, and he's actually a co-author in this paper. So, this is like, that's really kind of an update on the view of the thing. And this paper includes also a sort of a literature review. And this is to show, from the consortium to motivate, say like, well, this is actually a hot topic in computing education. So this is kind of, the colors are not so important here. This is sort of number of publications that talk about notional machines, or that sort of maybe show a notional machine, and you want to show that, oh, this helps with learning, or it doesn't help with learning, something like this. And we were hosting like a conference, what was it? I forgot which conference was it that we hosted in Lugano, and there was like a whole track of papers on notional machines and things like that. So that's that's something that people are interested in, and that paper there that I showed, it sort of went on and collected from practitioners various notional machines, and there they already tried to sort of have a standardized way to collect these things. And here's already the seed of the thing that I want to talk about. It's sort of like, well, there's got to be some kind of correspondence here between some things in the notional machine and some things in the programming language space. I actually forgot I was going to say something from the beginning, which is a thing that people kind of just say like that, but I was been thinking a lot about this, that please ask questions. People always, I heard this from the speakers, and I'm the first to think like, oh yeah, right, I'm never going to ask anything. But that's, yes, please, yes.
Yeah, so would, for example, the lambda calculus also be a notional machine then? What is the difference between, let's say, execution substrate and a notional machine?
Yeah, right, exactly. No, so my point is actually that, oh, yes, thank you. Yeah, woo, okay. The first one. Yes, so the question is, would lambda calculus be also a notional machine, and what is the difference between a language substrate and a notional machine, right? So, as I'm going to, my point is actually that there is a language-like aspect to notional machines, right? So you can sort of essentially cast this with the vocabulary of a language, right? And this whole thing is really how to think a little bit more formally about notional machines using the PL sort of terminology, but not sort of recasting the whole thing into it, but kind of trying to find this mapping, and I'm going to go exactly into this. Okay, so but that's the right question. That's the right question. Yes.
Are notional machines thus models?
Are notional machines models? This audience here, it's like, wondering, I'm going to say things that you already know I'm going to say. But Yes, that's in some way, that's another way that you can put this. I mean, so essentially, I think it was written in the abstract there saying like, look, what we want is to take well-established notions from PL and apply to this, right? To this world of computing education. And so this is a way that I think you can cast this problem. And you're gonna see, I'm gonna cast it in a certain way, and I think there are various ways that you can, and there's sort of a somewhat correspondence between these different ways of kind of casting, casting this. And yes, so that's good. Yes, exactly. So. Okay, good. So I was saying, let me just, yes, okay. Make sure I'm keeping track of time here. Exactly, so I was saying, there's already here some kind of an intuition that there's some kind of correspondence between these things. And what is the problem? What is the challenge? The problem is, let's take this one example here. This is a card that there's even a website that people are sort of collecting, the researchers from the from the paper we're collecting, etc. And then you have like array, a stack of blocks. So, I don't want to pick specifically on this. You're going to find other things that have a little bit of, the idea is that, and, in Matthias and Johan, they're actually co-authors in that paper too. And so that actually, this problem, this need actually came from them. And they say like, look, we have this and it all sounds good and everything, but some of these notional machines have an intuition that there's sort of, there's something that doesn't seem quite right? Like here, for example, you say, array, a stack of boxes. Well, specifically like the word stack, there is a meaning of this word, and there's a sort of implied semantics, and that you like, well, you access the thing in a certain way, and arrays, isn't the point of arrays exactly that you are accessing it randomly, and in stacks you're not doing that, right? And ultimately, the thing was really, ultimately, and that's really the thing that I wanted to say, is that you want to use these notions from PL to reason about notional machines. That's the whole, if I was going to say sort of in one phrase, my colleagues there even make fun of me. It's like, oh yeah, this is Igor's favorite phrase, a framework to reason about. So that's the whole shebang. It's sort of not only that you have an intuition that there's something that doesn't seem right, but how would you go about showing that maybe there is a problem here, or how would you go about improving this, in thinking more systematically about it. Yes?
Monad is a burrito. Is it a notional machine?
That's amazing. So the question was, the monad is a burrito. You always have these things like, what is a monad? Monad is a burrito. Monad is there's all this what was it, that book there, the Bartosz, right? Has a category theory for programmers, and there's this whole thing like, all the ways that people say what monads are, etc. So I got a question. So there's Sriram Krishnamurti from Brown University. He also does sort of this work like PL and education. And I remember he wrote an email at some point because Matthias was kind of presenting an early version of this. And we had a back and forth on sort of this thing of, hold on, the word is analogies, for example. Right, analogies and metaphors. How do these words relate to this thing? Right, that you're saying, well, is it an analogy? And then you have things like, well, but analogies. It's fine that the analogies aren't quite right, that they are broken, and things like that, right? And so I'm sort of so I would say probably these things are more like, the burrito, etc. Maybe they're more like analogies or metaphors or things like this. And I say the way that I kind of try to relate these words here with what I'm doing, it's more like you have these analogies and metaphor. They sort of inspire, let's say the creation of some notional machine. A notional machine is something that you would have. It would be a little bit more structured. That you go to the students. For example, a diagram is easier to think in those terms because you go and you say, look. You were showing this diagram is supposed to have some rules, and oftentimes they're not made explicit. And part of my thing is saying like, well, you should actually make that as explicit as quite as explicit as maybe a language, right? And as you're running this program, you say, look, this diagram is, you're not just putting lines around. You're actually, there are rules of these. There are certain kinds of constructs here in this visual language that, that are allowed. And so, that's how I think that it relates to there was going to be a question? Okay, no. Right? No. So no, yes. Sorry, there was a long day to say no. Right. Okay. So exactly. So I'm saying, so the challenge here is that you want to have a way to reason about them a little bit more formally. And the notion then that I'm bringing up, that I'm proposing, is this idea of soundness. So you have on one side, you have a notional machine, whatever that thing is, that we're going to need to make it more precise. And then you have like some programming language, and then you want to sort of connect these things, right? And there's got to be sort of, well, what is this relationship here, right? And then you say, well, maybe there's a language, maybe there's a modeling, etc. And so the thing that I'm going for here is saying this is a simulation. Simulation in the sense of, by simulation, if you're familiar with by simulation, right from Milner, and it's the same also notion from the work from Tony Hoare to say to describe to prove the correctness of abstract data structures with respect to concrete data structures, right? So you have like some what is the relationship between these things, and a notional machine would then be sort of an abstraction of some aspect of a programming language, or a simulation of some aspect of a programming language. And the way to, and sort of more concretely, what does that mean? This is going to look like something that is going to be, when you look at it, I want to see their face like, oh yeah, I've seen that a million times. So the idea then is I'm going to show this, this formal definition in the context of, what would be this sound notional machine, the mapping of simulation into the space of notional machines, and then an example of how we can use it to analyze an existing notional machines, and also then how we can use it to sort of design a notional machine from scratch that is sound by construction, right? Essentially, the construction of it is derived from this notion of soundness. Okay, so. Well, here it is. It's one of these commuting diagrams, which, yeah, of course, no wonder they're all. Okay, this is good. That's the reaction I was expecting. I was like, yeah, of course, So that's and of course there's then you could sort of recast this in a categorical approach, which is not not what I'm doing here. But so this is going to be, we're going to blaze through because it's like, yeah, sure, I've seen this many times. Okay, so the idea here is that you would have your programming language layer here, right? So here in this case, the vertices are types and the edges are functions, and then you have your types and functions in the notional machine space, and then there's a mapping from the programming language to the notional machine space, with these alphas, and then I'm going to essentially instantiate these a couple of times with these specific examples, and sort of shows, okay, actually maybe something hopefully something non-trivial came out of it, something like that. Okay, so what you have is like I was saying. So there's the notional machine layer, the programming language layer, and what you want is what I'm saying. I'm casting as this in this soundness condition is essentially, well, this is indeed a commuting diagram. Okay, no. Nothing unexpected there. So let's see here how we would. Let's see this is in a concrete example. Anybody seen these sort of alligator eggs? You did? Ah, okay, cool. That's good. All right. So there's this. Brett Victor. He came up with this. Well, he didn't. He didn't call it a notional machine, but I'm calling it a notional machine. So a game that you can play whose rules would then have a correspondence with lambda calculus, right? Let me just to check here. Who's familiar with lambda calculus? Let me see. My bet is, okay. Anybody? Raise of hands. Lambda calculus. Okay, 100% almost of the audience. I figured. Okay. So, okay. So You're curious. Okay. Okay. So the idea is, well, I'm going to go through the thing, and then that part there that just clicked was I'm going to go more in details. So here it is. So the idea is that the notional, as I'm going to show, the notional machine layer will be this alligator eggs, and the programming language layer is going to be lambda calculus, and this aspect, right, that we're talking about is evaluation, right? Because as I'm going to try to show quickly, if we have time after, you could talk about, again, notional machines talk about other things, type checking, parsing, other aspects. Okay, so then, yeah, exactly. So actually, what I was going to say before is, so what you need is, a formalization of one thing, a formalization on the other thing, and then a mapping, and then you see that the thing commutes, right? And so on the language level, that's easy peasy, right? So that's 101. We've got this. I'm of course completely ripping off here Pierce's tuple, tuple book. So the lambda calculus 101 here, and these are sort of. This is going to be our Haskell notation, in as you know, like this, what is it, literate programming notation. So semi-math, semi-Haskell here. And then, so here it is. So on the lower part is what you would, so it's what you would expect. If there's something that I'm not saying, you can stop me. But I suppose that here I should actually go a little bit quicker. And then on the notional machine layer, so that's the part that is new. So this game works like this. There are three pieces. There is a hungry alligator, an egg, and an old alligator. And the hungry alligator has a collar, and an egg has a collar. Okay, and the collar is going to there's going to be a meaning for this. Okay, and old alligators are always collarless. Then the alligators, they are organized in a family, and this is sort of a thing, they are under. So if there are alligators under these three pieces here are under the red alligator, so they are being protected. To say you're protected by the red alligator, and then you can say that these eggs are protected by this other alligator, and this is sort of also transitive. So you can also say that the red alligator is also protecting the eggs, right? This is important for this notion of being protected by. So this forms a family, and then here you have another example of a family where you have three alligators, and they're all sort of covering these guys, and here, and these things are aligned. So this is sort of like, one family, that's another family, and that's another family. Okay, and so if you had another family, it would be sort of in front here, as I'm gonna show in an example. Okay, and so for example, these two eggs are being covered by this alligator, and then these three families and the elements in it are being covered by that guy, etc. Right? Okay, and so here, and then there are three rules. Okay, so these are the pieces, and they're organized. You can think of in a board or in a plane. They're organized in this way that I described, and then there are three rules. There's an eating rule, a coloring rule, and an old alligator rule. Okay, so the eating rule, that is the more elaborate, let's say, is that so how do you get from that state to this state? So the idea, sort of the metaphor, if you will, sort of inspiring this move, is that if you have a family in front of another family, and then with an old alligator there in the top left in the first family. Whoops, my bad. In the first family, then the boss of the family, so the old alligator from the top, then is going to eat the family that is in front. It's eating the whole family. And then it's dying, because I don't know why they're dying, but they die. And then the eggs that are of the same color of that alligator, they hatch, and they turn into the family that was eaten. Okay? So what happens is that top alligator eats and dies. That's why it was supposed to be here, and it's not anymore. It died. And then the red egg hatched and turned into that was the family in front that was eaten, and so it turned into this this family here. Okay, so that's what you get in one step, or you could sort of there's an animation of like these sub steps happening. Okay, so this is the eating rule. Then you have the coloring rule. That is what happens is before you apply the eating rule, if there are any colors in common between the families that are going to be involved in the eating rule, then you need to systematically change the colors of one of the families, right? So here before you eat, they have red in common, and then you go and then you change all the reds to green here, for example. Okay, so that then you can apply the eating rule. Then you have, and then the third rule is the old alligator rule. That is, if you have an old alligator covering a family, and then you apply the eating rule here, and then the old alligator is covering only one family, and then the old alligator then dies. Okay, the purpose was to protect multiple families. And now it's protecting only one family, and so from here to here is the step of the old alligator rule. And okay, so these are the rules. And then this is from that sort of theory. So in the description there you have this, and then after you say, okay, so this is the correspondence with the lambda calc. So I'm going to go over each one with an example. So. So the idea here is that the hungry alligator. So this whole thing was like, just so you know. So the whole thing was like, okay, have this framework and let's try to apply to something that is already a little bit more structured, a little bit on a language that we already know. It's well known. Was it? Oh, my bad. Okay, sorry about that. Let me turn off the phone. My bad. So and so. There was even this theory section there that sort of was relating. So we're following this and then seeing, how to map this and seeing if everything's fine, if there's any problem, something like that. Okay. So, so the idea there, that's why there are the quotes. So I'm literally taking the description there and saying, okay, so, the idea is that the hungry alligator is then a lambda abstraction. So here, you have this, it would be a lambda, let's say S, lambda Z. Then you have a variable, an eggs would be a variable. The color would then be the matching between so the hungry alligator with a certain color and the egg with the same color. They have the same variable. So you're binding that variable. The old alligator is then parenthesis. We're going to see a little bit more, we're going to dig a little bit more on that. And so that's what you would get here, right? So you'd get a parenthesis on this, and then you'd have, alligators, families that are one in front of another one. This is not written there, but that's what I'm saying. So for families that are, in front of each other, you then have terms that are in front of each other. So that would be application. Okay. Then you have another thing that's in there in the description. The eating rule corresponds to beta reduction. So this is, you're eating there, and that's why it's sort of this elaborate story, so that you would get the idea of the egg hatching and turning into what the top alligator is eating, etc. Okay, so this is, your beta reduction rule. So this is the application. The families are one in front of another. And then you're eating here, and that's what you get. Okay, right? So far, so good. And then you have this another thing that's written. The color rule corresponds to overcautious alpha conversion, right? So the overcautious here because here you would have to change the color because you are. You want to avoid this thing to be captured here, right? So the F appears here, and you don't want it to you don't want to capture the F that you are applying to. But here you wouldn't need to, right? Because T is not, there's no binding with T here, so you wouldn't need to recolor but you're essentially saying, well, if there's any color in common, let's recolor that. So that's equivalent of like, let's rename it in a more conservative way. Okay. And then the old alligator rule here would be that, well, as it's phrased there, if you have a parenthesis around only one term, then you don't need the parenthesis. Okay, so that's how it's phrased there. Which also, at first glance, it seems about right. And then we're going to kind of try to be a little bit more precise, right, on this and see exactly how that maps there. So here it is. We have our lower sort of the programming language layer here. We need to figure out the top part. So this we're gonna say, well, the A on the notional machine level. We're gonna say it's got these constructs there: an egg, a hungry alligator, both with a collar, and then an old alligator. And then there's this list because they need to be one in front of another, right? So that you would know, who's eating who. And then here, okay, so this is what you get on the top, and then we need to figure out this alpha, which it's somewhat one-to-one here, except for the old alligator situation, right? Because what happens here, and that's the thing that maybe sort of also when I looked at it and sort of at first kind of, because the thing is that the parentheses there are construct in the concrete syntax tree, right, of the language, not in the abstract syntax tree, right? And there, when I'm modeling in the alligator space, I'm saying, well, there's this construct in the abstract syntax tree of this language, right? And that's sort of the mismatch here. And another mismatch is sort of a mismatch is not as in it's wrong, but I'm saying a thing that you need to map carefully. Let's say that's what I'm trying to describe. And also that application, that you don't have an explicit application term, is that the things are, the fact that they are one in front of another in this list is that what you're applying to. And then, of course, all of this provided that you have some kind of magic way to turn names into colors that I'm hand waving here. Okay. Okay, so that's we're here, and you see that I said this abstract syntax tree of the notional machine thing, and so this is a parenthesis that I think it's worth sort of talking about. So what we're doing here is in this diagram you have the abstract syntax tree of the language, on the lower level, and then you have this what I'm calling the abstract syntax tree, the abstract representation of the notional machine, right? The types on the top, which are different from the concrete representation, both of the concrete representation of the language and the concrete representation of the notional machine, right? And I got actually very lucky because in the presentation of the alligator eggs, Brett Victor writes there, it's useful also to have this, you can do this in pen and paper. And I find it hard when I'm looking at something like this that is sort of like, well, okay, but what is the nesting? And when I write it in what he calls the schematic form, with these sort of, in pen and paper, and the hungry alligators are these lines with little eating thingies. And the old alligator, well, there's no example here, but there would be sort of these lines without a mouth here, right? And it's, well, maybe that's a good notation to sort of see what's the hierarchy, what's inside what, etc. And that's exactly an example of having a different concrete syntax, for the same abstract syntax, right, of or abstract representation, as I'm calling here, of the notional machine. So that helps with this, with this path of thinking more rigorously about a notional machine. And that's also what I was alluding to when I was saying, well, maybe you have this memory diagram, and actually these are not just some wiggly lines that you're freely drawing around. You know, they are actually, oh, okay, this box is actually a box that represents this specific thing. And these things have to be in the right places and they relate to each other in this specific way. And these underlying rules, they are, of course, in the abstract representation of this, you know, of the notional machine with its corresponding, you know, semantics described by those functions there. Okay. And so now we're back here, and there is one little detail here that before getting to the kind of the punchline, let's say, which is, you know, we did this whole thing. I talked about alpha, and now, you know, there's this the top level guy missing there, and what we want is I talked about these rules that sort of show how the game evolves, right? And so, you know, let's say the first intuition is that, well, you would just apply these rules. You apply them, and that should do the trick. But one of the problems here is that they don't have a one-to-one correspondence here with the evaluation rules, right? So, for example, the old alligator, we saw that the old alligator is not a construct in the abstract syntax of the language anyway, and so if you do a step involving that thing, that doesn't correspond to a step in the lower part, right? And so in the lingo of by simulation, this is to say it's not a lockstep simulation, right? It's not a one-to-one step on both sides, but that's fine. Actually, part of this whole thing was sort of how can we find a formalism that is sort of as forgiving as possible, sort of as loose as possible, but that still captures a sense that these things, that there's a correspondence here that if you violate, then it really seems like there's something wrong, right? But that you don't want to be too stringent. So in this case, one way to sort of go around this is to say, well, let's do a fixed point of all these rules and get to the end, or in another way, as you know, is let's do like a big step semantics, something like this. This is another way that you could think about that, right? So let's just apply all these rules up until we get to the end, and so in the lower part, then instead of step is an eval. Okay, so this is, and then to do this thing here. One thing that you want to, then the next step is, I wanted to do another slide here, but I didn't. So, so another important thing here is, okay, I think it's all ready, and what are you going to do? So you can, for example, mechanize this proof. You can sort of implement these things in Agda, for example, and kind of do a mechanized proof, right? Or you can do like an equational reasoning proof with, in Haskell. And this, as I said, this is sort of sitting in between, SIGPlan and SIG-CSE. And so, even though I'm very excited about the idea of writing it all in Agda and doing Agda proofs, one thing that I wanted to say is essentially you get the benefits of, as I was saying, sort of this way of reasoning about notional machines, even if you don't write proofs, right? And so part of when it is like, well, you can sort of do a semi-formal reasoning of it, and another intermediate step that you could do is what I did in this example here. You could do property-based testing, for example. You say, well, what about doing property-based testing? I'm going to write this here, and I'm going to get these things being generated, and then, I'm going to write a test, and that's sort of sitting in between that you say, in between what would be like really writing a proof, or kind of reasoning in a more kind of, back of the envelope kind of thing. And so to do this, then, okay, let's say we do this, and then then we're going to get one last hurdle, which is, nope, sorry, not yet. One last hurdle, which is, to compare these things here, you turn a variable into a caller, and then on the lower step, you do a substitution, and then what happens? you do like a variable renaming, for example, right? And then you turn the thing into some other color, and then you want to compare the guys there, and then you're comparing different colors. You have problems like how the hell you're going to compare the colors. And there is also a well-known solution for this, which is using De Bruyne indices, right? You can you say like, well, we didn't need names in the first place, right? And so what we can do is do this this alligator De Bruyne thing on the top, right? In which you you turn these things into punctors, on colors, and then you do a De Bruyne transformation that does essentially, there's a canonical representation, right? Where instead of colors you use numbers, and then you do the same thing here on the bottom, so that even if you have different colors, you in the end, of course, you have the same De Bruyne representation then. Okay, now I think we are finally good to go, and we are here, and we write these properties, and now we're finally good to show an example where the thing is supposed to work well. We're good. There's the theory mapping there. Everything seems fine, and then boom, then there's a problem. And so I was I can't begin to tell you how surprised I was when I was writing this, and I'm absolutely sure that there's got to be something wrong with my implementation, because after all, I mean, how much more do you want? You know, this thing was sort of like there was a one-to-one mapping seemingly with the theory there, and maybe you're trying to guess here. Don't guess yet. Don't. I'm gonna of course, you don't need to understand this. I'm gonna map this into the concrete examples there. And so here it is. So what happened was, now I'm writing specific values here, right? Instead of the type. So on the upper part there, we apply the coloring rule. So the top alligator, eats, and then the hatch with the same color hatches, and then you get that guy, right? That's what I said. That was, the top alligator eats, dies, and then the egg with the same color hatches, and you get this. And if we do lambda t, and you apply to lambda AA, you get lambda tt, of course, because, this t here, as we know, refers to this t. It doesn't refer to the other t. And so that the term, that's not the same, right? So that's what happened. That's what happened. And so specifically, when we look at substitution, again, completely ripping off Pierce's, tuple there. I even took the exact examples, that they have there. So this is, this is an example of the thing doing what you think, because, none of the names clash. But there are two pitfalls. One is the variable capturing that this recoloring is supposed to address, right? That is, if you are substituting here in Z, there's the same variable, there's a free variable here with a binding here with the same variable, then you would end up capturing this. So you definitely don't want to turn this guy into, an identity function unintendedly, right? But the other problem, which is the problem that is not addressed by recoloring, is that you should only substitute free variables, not variables that are bound, right? So if you're substituting x by y here, you definitely don't want to turn the identity function into something else which wasn't an identity function, right? And that's not, recoloring is not going to help you with that. And the thing, and also there's nothing wrong with the guarding thing about this. Say, well, but then because this egg wasn't being guarded, it has to be transitively guarding the thing, otherwise you wouldn't reach the egg down across other guys, right? There's the problem is a little bit more subtle here, and so there's some suggestion. So that's what happened here, right? Whoops, my bad. That you were. Like I said, so the red, this T here was already bound, which means that the fact that the two alligators had the same color there was the problem, and it wouldn't, and they don't have a common color with the green ones, right? And so a couple of possible solutions here would be, so this is the text there describing the eating rule, is that, instead of saying if the alligator is guarding an egg with the same color, you could say that they're guarding an egg with the same color that are not already guarded by a closer alligator with the same color, for example, right? Or you could, this is sort of kind of trying to make the smallest possible change that I could think of. You could also restrict the colors of the hungry alligators in a family to be all distinct, right? So that you wouldn't have this situation. So you would sort of also say, well, it's these colors, they have to have a certain pattern where they can't be the same. Or you could then, of course, I was already talking about the De Bruyne indices before, right? And even in the description there is sort of not an alternative present day, but there's like a little sort of mentioning, not to prevent this problem, but there's a mentioning of saying, well, you could, instead of use colors, you could say, there's a family hierarchy thing, and so there's a father and then a grandfather, something like this, sort of an age sort of hierarchy that would be like a De Bruyne index kind of thing, right? And that's, so this was indeed alluded there, although not to solve this problem. I mean, this problem wasn't pointed out there originally, right? So yes.
So if you go the second route, then essentially some of the lambda terms would not be represented, like not faithfully represented.
Right, exactly. So this is sort of like all the sort of ways that I'm thinking within the rules of this game that you could make changes so that you would avoid the specific problem. But then you say, well, but this kind of this kind of restriction on variables is arbitrary. That's not how we want to actually have the variables the way that we want them, right? We want to be able to write variable, and we want to understand that that let's say the inner t there is actually bound by the closest t and not the other one, and this should be then that would be, that's why I favored sort of this other change here. Although one's going to say, well, the rules are already seem to be very specific and somewhat contrived. They get even more, specific maybe. But that's not the point. I mean, my point is sort of like, well, essentially, you take something that seemed, that it was already had a more precise description than other notional machines that were out there. One that seemed to be okay, I mean, this is as good as it gets, right? And you still find some issue that is subtle, some issue that is not super apparent. You could read that and so like, yeah, sure, that's it all seems good. I mean, we went in super detail here, and I don't think that it would, so I think there are a million ways that you would sort of make mistakes in trying to come up with these notional machines in general, and that's actually part of the point. That was my point that I was making from the beginning. That is, you want to have a sort of a way to reason about these things that are then, of course, depending on the how rigorous you want to go, then maybe you catch more things or less things, but, even if you're sort of just from the top of your head sort of thinking like, well, I'm thinking of this thing, how would that map to this diagram? You'd be surprised. I mean, I think you can already improve if you're, the design of this notional machine. You're coming up with this diagram or this or you're trying to sort of instantiate, let's say, a certain metaphor and make it a little bit more rigorous. Oh my God. I'm going to just rush through a couple of other things here, which was the other thing that I was going to say, but which again, it's not going to be any news for you, which is, well, what I did is there was a new thing, and I said, okay, let's try to, map this here into this thing and see what we get. But of course, what you could do is say, well, can't we kind of build these things from assuming that the thing commute already, and you say, well, yeah, of course, let's say the simplest sort of construct is, if this mapping here, if there's actually an inverse function of this alpha, right, then you can define the operation in the notional machine level to be one that actually goes around, and so then, of course, it's going to commute, right? And you kind of do that on purpose. There is no, you don't come up with another. I'm not saying that you should do this. I'm saying you could do this. And then you would have something that obviously works. And so let's say an example would be, I was talking about this expression trees in the beginning, right? And so you have there, the terms of a language, and then you have, a one-to-one mapping, for example, from the AST to a visual, a construct in your visual language, and then therefore alpha is trivially, you can invert it trivially, and so, each one of these steps is, there's no other thing. You're sort of, you are, so this would be something which is this thing that I'm calling like there's an isomorphic notional machine. And even if you don't do that, if you have another useful situation is where you have something where this alpha A there's a left inverse of it, right? So what you have essentially is you have a notional machine where there are states that are not representable in the language, right? But if you started from the right thing and you got the right representation, then you know that you can come back, right? So let's see an example here. We have this is actually a tool that we have online. I'm just getting just a little screenshot here that is like an expression tree, but the tool is called expression tutor, but what happens here is this is actually the data structure behind is a graph-like thing where the students can put the nodes there and then they can connect holes, any hole to any other hole, okay? And so then, and this was inspired by, Matthias was for a long time doing, using expression trees a lot, even in exams. So you say like, oh, draw the expression tree of this expression here, for example. And then you would get, and of course this is not like, this was practice in class and, and we did exercises, and you'd still get all sorts of crazy things that you wouldn't believe, right? And there's a common thing in education that is like a pitfall that you say, well, I'm coming up with a tool that it's going to be great for education and it's going to handhold the students and they're not going to make mistakes. And you get to the end and it's like, yeah, look at this. It's all great. Yeah, of course. I mean, they couldn't make any mistakes. So they're kind of, it's more like a next finish kind of thing, where you're kind of being guided. And so this was like, no. This is actually, that's not a bug, it's a feature, Let's do it in a way that is a tool that allows them to make mistakes that are closer to what they would, the things that we see in pen and paper, that they can actually, this thing doesn't have to be a tree. They can connect, that they have to make it such that it's a tree, and that's part of the point, that something that they're supposed to learn. And if they connect the things wrong, then it's wrong. And we have sort of like, can't we, and then we have a thing, for example, for Java that analyzes Java source code and it generates this tree, and then they plug the things manually and we sort of compare them, and we show a mistake and say like, oh no, this doesn't correspond, there's something here, do it again, something like that, right? And so in this case, because this thing here is actually not a tree, it's a graph, then you have, let's say that it's represented by this type there, expression tutor diagram. If you actually generate it from the tree, then you get the tree, and so then this one is right? And you can use a maybe or an arrow type, something like this, to just say, well, if it's done wrong, then of course it's not gonna, but let's say it's not gonna correspond, but the diagram commutes because there is this a way around here, right? Essentially, that is not a way around like this, but a way around, through the maybe or whatever other type that you're, whatever other burrito you. So exactly. So this is it. So we've done. We apply these with varying kind of degrees of rigor to different notional machines, different programming languages. Some of these are actually sort of also, they correspond to that sequence of languages from TAPL, the sort of, if you want to say, what's the simple language to talk about types? So you have this type arithmetic expressions, right, in the early on in the book. But we also, we did this because then we can do sort of, complete things with languages whose semantics are well established. But we also did, like I was describing, expression tutor for Java. for essentially a subset of Java that is the subset of expressions up to Java 11. And also sort of to show that you can use it for different focuses. You can talk about memory, references, you can talk about type checking, parsing, etc. Right? So that's the thing. And I wanted to sort of do a final plug here on our research group there, right? The Luce, the Lugano Computing Education there in Lugano, led by Matthias Hauswirt. This is our guys there, although I recently left. but yeah, so there's a great work also done by Luca on there was a big teacher training for the high school teachers that are going to teach informatics in Switzerland, and so Luca was also doing. There is this platform, Pythamara, to teach programming focused on graphics. So essentially kind of focusing on function application, function composition, and a little bit inspired by the Haskell diagrams library, things like that. So yeah, that's pretty cool. That's it. We're on. Cool. Yes. Okay. Any questions? We had lots of questions during it, which was good. Hope I didn't lose people. Yes.
What other notional machines did you consider in this work? So you saw an in-depth treatment of the alligator.
Yeah. So there's also another thing. There is a set. So this is almost all of it. There is another set of things that I didn't mention here that I wanted to have. I forgot. That is, you can also do that for data structures, right? So the whole thing that I was saying before, the arrays or stacks or things like this, and actually the original work on Notional machines was like the examples were things like lists or arrays or data, data structures, and of course, and also when I mentioned in the beginning this Tony Hoare that said, oh, that's a way to prove the correctness of abstract data structure with respect to the concrete ones. So like, yeah, of course. So this works. So the difference is that instead of the language layer, what you have is the data structure part. The operation there, instead of being evaluation, are the functions. They are the operations of the data structure, right? So the data structure sort of allows certain kinds of operations. Let's say an array, you can allocate, you can index, you can dereference, or a map or whatever, a queue, you can queue in queue, etc. And then you can have the notional machine layer is essentially some representation that you can come. So for example, the original thing was, I think the first really paper that had a thing with notional machines was talking about a list and then what was it? I forgot the name. These piles that when you're kind of in a warehouse that you have a car that sort of carries things around, right? And that you can have, so even if you don't have boxes, you have the base thing, right? That you're carrying around, and so that was sort of the empty list, and you can kind of then put the other things around and think. What? Sorry? Palette. Yes, that exactly. Thank you. Yes, that's it. So then I also had examples of data structures. Yeah.
And for data structures, it would then be operations on the data structure.
Exactly. So the what I said, the language layer is then a data structure layer. The operations are the function, this transformation layer on the function on the language layer are then the operations on the data structure, exactly like you said. Yes. But on the part of the languages, these are the notional machines. There's also the right now actually we have an intern that is we are submit just I don't know if this is going to go through, but just had submitted a paper to an education conference on a thing related to Python tutor that had like a somewhat inspired by also an expression tree, but evaluating the thing and showing intermediate results, and this is because we have this cards that are printed out. So the students in high school and also in primary school, they are using this platform. And one of the things is we have like a paper representation of nodes of a tree, and you sort of, put them on a table, and we connect with a line and things like this. And we had some high school teachers using this. And then the idea is that we're having like a tool online to kind of, do this. And this, and we were sort of doing. So in this paper, this paper that we wrote is for an education conference, so it doesn't include that. But the guy that was Nathan, our intern there, he had sort of courses with Coq, etc. And so he got excited about this thing, and I said, "Oh, so we have a sketch of a mechanized proof, for example, of this in Coq, and this, and it's nothing that you would, nothing out of the extraordinary. It's essentially, following these things. But then, you want to also have parts of the tree that are evaluated, even if there are problems in other parts. So you want to talk about like programs with holes, right, which is a work that already exists, also in Haskell and things like this. So we kind of, that's the thing that is a little bit non-trivial there, let's say. And then it helps to kind of also think about this, like, oh, but if this is evaluation and then there's a problem in this program, what does that mean that you still seem to be evaluating it, but, and there are problems. And so all that sort of helped to kind of guide this kind of this thinking. Yeah.
Having seen the examples of notional machines that you showed, I'm sort of at least intuitively getting the feeling that in all of those, at least for a correct notional machine model of some concept, there is a bijection. Is that always the case?
Yeah, no. Yeah, so that's the thing. Oh, my bad. Yes, thank you. Yeah, I also didn't repeat the other question. That would be so the question was that by the way that I presented, it seems that when the notional machines are correct, there is a bijection, right? And that is that's a wrong implication from my presentation. No. So the thing is, no. So what happened was, actually, in the first one, we showed how we could change it such that it would commute, right? And there was there wasn't a bijection there, or at least when I built it, I said it doesn't have to be, right? I didn't build it based on the thing doesn't commute because of the functions on top, for example, they are on the world of the pieces of the alligator thing, which include, for example, the old alligator rule and all of those things, right? So they are not going around, right? The isomorphic case.
You could come up with. I have the feeling that you could come up with something to kind of make it a bijection.
No.
In certain cases, right?
Yeah, right.
I've introduced the parentheses where necessary.
Yeah, right. Exactly. So I figured that I was imagining that this was going to come up. Yeah, exactly. So I'm not. That's why I was kind of correcting myself there, as in like I'm not saying that you can't make a bijection. I'm saying that the way that I presented it. It was an example to show that you don't have to have that, and that was part of my intention originally. I'm gonna get there. Hold that thought. That is, I wanted it to be as flexible as possible to sort of say, well, it doesn't have to be. Actually, part of the thing was. Oh, I looked at that. Isn't it cool that, these things can automatically be done and you don't need that? And it's like, well, but then if this is it's a bijection, then what is this value? Maybe there's nothing here. Maybe this is just a visualization. And then there's also this work on visualization and live programming, a bunch of other things, right, that maybe connect to this. And so, so I think it's an important thing that that's not a requirement for the thing to work. That's definitely not the case. But it's true that I didn't have a lot of examples of things that I did that were not like that. But that wasn't.
But there are such examples.
Well, I mean, the alligator, for example, was one that when I did the whole thing in the end, that was an example that wasn't the case. I think the reduct. That actually I don't completely remember right now, but it's because there's a paper on reduct. There is also a game that supposedly helps to show how programs evaluate. That it's even further away from from, there were other, it was harder to kind of, well, hold on, this one here doesn't seem to be, right, etc. And it was another example that was like that. There was you take a thing and then you try to sort of implement those rules as they are described, and then maybe there's some problems and you sort of massage them. So that would be another example. Yes. Hold on. Yes, there was a question.
About the previous question, doesn't the more complicated diagram with the maybe show that it doesn't have to be a bijection?
Right. So the question is, doesn't this diagram here with the maybe show that that it doesn't have to be a bijection? Yes, right, exactly. But still, I'm thinking that you also that you kind of imply, or at least I imagined you saying in my mind that essentially like that for it to be good, there has to be a relationship between these two things already on this alpha here, and that the examples that seem right are those where they are tightly connected, either because there's a left inverse or there's an inverse or something like this, right? So I said that these are cases that I think would happen very often, although I'm using this word very, very loosely, as in, I'm not attaching a number to it. but let's say out of intuition and experience, that seems to be, often the case, but that's not a requirement, definitely, that the alpha be either an invertible function nor left invertible or anything like that. And then, yes, there was another question, yes.
So obviously it's very rude of me to be asking a question that I missed the first 5 minutes.
No, please do. That's
there. But, I was also thinking of, I don't know if you're familiar with Smolian's Mockingbirds example for SKI combinators. There's a little bit of a story.
Oh, right. Yes, I've seen a presentation of that, but I don't have it in the back of my mind. No.
It's very, very cool. The thought is something like, when you look at this commutative diagram, you could have SKI on top and lambda calculus on top.
Right.
But there's nothing that corresponds to like function application, right? Like, so is part of the, again, I missed a little bit of it. Maybe you answered this, but is part of the idea of a notional machine is it that the connection is supposed to be a bit tighter, and therefore, for instance, the app of the alligator when applied to, the app of the terms when applied to two terms, if you sort of map the terms individually and then map the app as well, then that should be, the same thing as mapping the result of the evaluation, or something like that, where you sort of see the structure in a way that's clearer than would between SKI and lambda, for instance, right? Where I don't know if you feel like SKI really illuminates calculus in the same way that the alligator.
So the question is, I'm getting good at this. The question was very long. It was about, what is the relationship between the SKI combinators and lambda calculus and this work with notional machines? Would that be a notional machine, and does it have to be, how tight does it have to be, the relationship between the language and the notional machine? And does it, for example, does it have to have an application and also an evaluation step? Do you have to have an evaluation step, etc., right? So first, I want to say that I don't remember very well the SKI, the Mockingbird guys there, right? But I can say that. So again, originally, just as a kind of guiding sort of idea, is that really what you want is for this to be as least restrictive as possible, and still say for it to be useful and to seem to describe that, let's say, that really there is something not quite right with a notional machine if you don't have even that, something like that, right? Now, having said this, for example, and again, I show some examples here, and that didn't include all the things. So, for example, you say, well, you see here, these types are the same, but do they have to be? They don't have to be the same. You can have something where the types are different. You can be also these functions are. Where's my I know what happened, because when I clicked, it probably lost the focus. So this other thing here is the focus, which is what I wanted to say. So it doesn't have. Another thing is, it doesn't have to be, like I said. A notional machine doesn't have to be about evaluation. It can be about type checking. It can be about other things. So this means that those functions there, they would be different functions, maybe talking about types, or they would be, and then in the case of data structures, there are different functions. It's not only one function. There's one function per operation, for example, in the data structure, right? So there is a bigger space of possible diagrams that all kind of adhere to this thing that I didn't show. So yes, so that's what that's kind of the general answer without answering for that specific case that I don't know. That's the thing. Yeah, but that's the general answer. So essentially, what I would do is, okay, interesting. Let me look into this. Let's sit down. Let's see. Let's try to instantiate this thing and see what it would look like. And then, for this, and then maybe there's an interesting insight there that, that maybe something early on doesn't seem to matter, but then it's like, oh, look at this, maybe there's that thing. And at least, let's say, again, as an anecdotal experience of doing this, like every time you seem to have an interesting insight, it's like maybe something doesn't seem to work, but then it actually works. It's just that you're not thinking it, you're not thinking in the right way. Let's say, in the case, for example, of the work that I didn't show here, that with these trees that are that I was talking about, like that show partially evaluated expressions and things like this. Then we say, okay, so the thing here is that this operation, this correspondence, is not just one step in the evaluation. Otherwise, if there was a problem, you couldn't evaluate the whole thing. This is more like what you're doing is you're mapping an expression to the derivation tree, because that's where you actually have all the sub-steps of all of the things, and you have information about the sub-steps that actually work, and you can do that for type checking or for evaluation, right? And so even if part of the tree, if there's a problem in part of the derivation tree, the other part is, something like that, and so there was always some kind of insight to be had, and something to be adjusted, or, so it's hard, let's say, so essentially, it's very hard to kind of answer a question for a specific example without having tried it. Yeah, that's what I wanted to say. Yes.
I have a question about rotational machines in general and your alligator example.
Uh-huh.
I don't know. Maybe this is just me, and it's good that I'm not recorded. But maybe it's good. Maybe these alligators are not the best notional machines for lambda calculus, but I haven't found any better notional machines for the lambda calculus except the lambda calculus itself.
Uh-huh.
I don't know. So question one. Is there a sort of a qualitative or a quantitative degree of saying, is this notional machine good or not? You just said if it's sound or not, but what about the goodness category?
Right.
Is there some research on
Yeah.
this? Number two, does your soundness proof somehow give me an index into how good this is?
Right. No, that's a very important. So the question was, I'm here, I'm talking about soundness, but does that mean that it's good? Like, as in, maybe a certain notional machine seems to be contrived, it seems to be not a very good notional machine, using another sort of, there's some other way to evaluate it that is not being captured here, right? And that's a very, very important question, and I'm going to cast it a little bit in a different way, right? Which is, I'm gonna say what I think you would, what you were saying with the sort of my hat on from the from the computing education side of things, right? The SIG CSE side of things. So the SIG plan side of things is going to say, well, look at this, I have a soundness thing, and then I have the proofs, and everything's fine, and it's beautiful, let's go home. And then the SIG CSE parts are like, well, the way that they would say is, or the way that I would say with this hat is, okay, but does it help with learning? So all of the most of the focus in the publications in the computing education conferences, let's say the crown jewel of sort of the let's say if I were to do it in a caricature, sort of the crown jewel and the SIG plan side would be. We have some kind of soundness proof, or we have some statement about a formalism, let's say a type system, and then you have a proof, and that would be kind of a typical example of a publication, right, in that realm. And in the computing education side, the crown jewel there is the learning gains, as we say, right? That's like say I'm kind of of course there are a bunch of other ways to do research, but that would be a typical way that you say like, look, I'm coming up with something. It could be a notional machine, it could be a pedagogical approach, it could be God knows what, right? A tool, and what I want to measure then is, do they learn, right? Does it help with learning? And then let's say the way to do this would be, you can do an experiment with people that use the approach, don't use the approach, and then you try to measure some learning gain, or you can use some kind of proxy measure to try to do that, etc., right? So, right, did I get it right? As in, like, what you want to know, is it good, right? As in, like, good. That's normally the measure that we would be looking at from the point of view of education. And having said that, none of that is here. Absolutely none of that is here. That's very important to state. So, the thing that I was interested in is that all of the research that already exists about notional machines, that's mostly focused on that, on learning and saying, and all of that, which is absolutely essential. And none of it, I would dare to say, sort of talks about, well, but we know that languages are formal entities, and you're sort of describing some systematic device that is supposed to be talking about these formal entities. And so then, I kind of like, there's an itchiness here. There's like, well, there's got to be therefore a formalism between this formal entity, which is a language, and this device, right? And now, what is then the ultimate question is then, what is the relationship between these things being sound or the soundness and learning, right? Does it help with learning, or something like this? That would be something that one would want to do. That I don't have that, but I think that would be sort of the ultimate question. I can say that. Learning gain research is very difficult. I mean, it's as you know, it's kind of like also in psychology, sort of experiments of this kind. There's a lot of variability. There are all sorts of things that that impact the thing, your numbers. You can look. Actually, had a bunch of sort of research also on the always going. On the sort of, he even had one where he did an experiment in a traditional way, and then he kind of said, well, look, given the specific situations here, you can sort of interpret this data in two different ways, and you could essentially make it show like there is learning gains or there aren't learning gains, with the same data here, given some not forcing the an interpretation. Essentially, with good interpretations of the
Would not an easy proof say that it's a better notional machine because it's clearer, more elegant? I don't know. Is there something
Yeah. So that's the thing. I mean, the thing with the better thing, I always sort of, because normally it kind of goes in the direction of the learning gain. So I really kind of avoided making any, statements of this kind. Simpler proofs are, so there's some work that also inspired me here from Connell Elliott, so he says certain things like, what was it? He says like, the theorems have to be simple, but the proofs can be complicated. That's fine, so we can check them with a machine, but the important thing is that the theorems are simple, So it would seem like, let's say, there's an intuition that, if you had things that the proofs are simpler, maybe that would seem like a good idea, but maybe that's not a requirement. I'm not super sure. Yeah.
So what's the takeaway? How do I design an optional machine?
Right.
I don't want it to be isomorphic, right?
Right. So so the way that I was casting this was saying, if you want to design it in a way that is sound by construction, then you want to do one of those two constructions there, right? But then, of course, as I was saying here, that's not a requirement. And then you say, if you don't do it this way, is there a way that you can be guided, or something like this? So what I say then, the best that I can say is the commuting diagram. This is your guide, as in what you want to do is you would come up, let's say, with your let's say you could call it in this example of delegated the game with the rules of the game or something, etc. And then you would the commuting diagram would be the thing that would then be the guide, but it's not a guide as in it's not like the other case where it gives you something, right? The example of the thing that was isomorphic and say, well, you follow this and then you get, then you already get the other step done, right? So it's not a guide in that way, but it's essentially what I'm going to say is, having a formalism to think about, let's say this is the guide really, because essentially if you didn't have that, you wouldn't have anything, or let's say there's a bunch of notional machines that are done that don't, let's say none of them actually use anything like this. They are thought out of intuition, they are, and then and they seem to be right, and and so that's so it seems a cop out that I'm saying the diagram, the diagram is the guide, but actually, if you think about sort of the state of how normally research is done, or notional people come up with notional machines and publish, etc., they are actually there is nothing there is no as I call it, sort of a framework to reason about them or anything like that. So that's. Oh, the question. Yes, I forgot to repeat the question. Okay, that was that. I thought. Didn't repeat the question. We're over time. Okay.